First off, I guess the question that I would ask is why add more complexity to what is, fairly complex systems and hydraulic systems, right? You already have lots of different controls, valves, heaters, filtration, all sorts of things going on in hydronics. Why add more complexity with solar thermal? More things to break, more things to fix, more things to keep track of, right? So I guess there's maybe one reason. So fossil fuels are great, generally what's used in hydraulic systems. Right? They're controllable, they're storable, they have very high intensity, and they're very transportable. Right? So we love about fossil fuels. You know what they are, they're very energy dense, and you can move them around and take advantage of it fairly easily. Solar energy, however, cannot be controlled. Can't say when the sun comes out, when it doesn't. We wish we could. We do know it's coming up again soon. Hopefully. Right? So we know it's difficult to store, right? It's generally not there when you wanted it exactly. Very low intensity, right? The actual power of the sun's very low, but it's the entire world, so that's why they're getting that low. It does not match the location or the load exactly, right? Usually. But there's one really good thing about it, and that's that it's free, right? The sun's there for all of us, for all that we will use its energy to its best potential. And not have to pay for it as a gift. There's also additional challenges if you are considered that sort of thing. I am. And so, we have different challenges as far as dependence on imported fuels, right? Fossil fuels are a finite resource. They may not last forever, maybe for my lifetime, but who knows beyond that. We do have climate change concerns. The best thing about solar is that it's free. Right? Once we put in the effort in order to install equipment and systems that can take advantage to it, we don't have to continue to pay for that fuel source. Right? So let's talk about what is solar heating. Right? Solar is a word that's thrown around a lot and it can mean a lot of different things. So there's generally two different types of solar energy. There's solar electric, which is photovoltaics or PV. You've heard of that. That's where you take solar energy and you're producing electricity from the sun. We're going to talk more about solar thermal. Solar thermal is where you're using the heat from the sunlight for heat, converting it to another sort of energy type. They're two dramatically different technologies. They work very different. And so I'll just have to go through fairly briefly. But solar electric, or photovoltaics, is producing electricity from sunlight. And how it does that? It actually has a doped silicon PN junction, which produces current when sunlight hits it. Right? When you have a load, such as a light bulb or anything else, then that will draw the electric current through the circuit. Right? So, however, solar thermal, which is really the oldest form of solar, is a little different. First people that introduced me to solar thermal, his name is Paul, so I call him Ocean Moss because he taught me how solar thermal worked. And it's pretty basic. So he had three physics of solar thermal, and the first law was it's a black pipe and the sun makes water. And we've all experienced that when you're a kid. You have a black hose in the sun, you go to take the leaf from the hose, and it gets yourself, right? Works really well. That's the physics of it. It's not too crazy. More black pipe and the sun makes more hot water, right? So if you want more energy out of the sun, you just put more stuff out there to collect the energy. And a third one, which is you put black pipe under glass and make hot shower, then you can get temperatures in which we're going to miss hot water type temperatures. Go on in, please. So this is, I spent a little bit of time on this chart, but I think an important differentiator, right? Why choose a certain solar technology versus another, right? If you're producing energy from solar power, right? You really want to use the best one available for the application. So this graph here, I hope it's clear enough for everybody, kind of shows solar thermal flat plate technology and PV, kind of your standard polysilicon cell technology. So to the left, you actually have a temperature differential, so solar thermal is fairly interesting. The efficiency changes also based upon the temperature. It is ambient, or how they're rated at least. They're rated the ambient temperature and the temperature coming into the panel, right? So that changes over the course of the day as you're generally heating a tank hotter and hotter over the course of the day, that temperature differential gets bigger and bigger, right? And so the efficiency starts to decline. But the beautiful thing about solar thermal is that you end up at such a high point to begin with. Since you're not converting, what is radiation into, some other source of energy, right? Keeping it in the heat spectrum. You start out with a flat plate solar thermal collector, if ambient equals inlet, usually around 75 to 80% efficiency. So that square footage of that collector, of sunlight hitting it, available sunlight hitting it, you're able to convert that into heat, right? So with photovoltaics, right now there's around a 20% and 25% is what the efficiency is per unit of area. So quite a big difference, right? PVs do decline in temperature. The hotter they get, the less efficient they are. But same with solar thermal, right? You start losing more heat to the environment and things like that. But you can see in what I've kind of highlighted in the orange is up to pretty much 75, 80 degrees over ambient temperature. That's kind of your domestic water heating and your radiant heating sort of spectrum, right? So if you see if you're within those ranges, solar thermal technology on a per square foot basis is still about 3.5 times more efficient, right? So if what you need is that heat energy and what you have is limited space, which we generally do, we're working with confines of something, right? Then solar thermal could be a good choice for you, for your project. I guess kind of just breaking that down, if you're familiar with the PV world, that makes one of the SunEarth TRB collectors in the same footprint, about 2 square meters of a PV module, 1250 watt module. So there's different types of solar thermal technologies, and we're going to kind of stick with what we call medium temperature technologies for hydronics applications. You have glazed flat plates and evacuated tube type collectors. They both basically work the same. They have glass that exposes a highly selective surface to solar energy. Their pumped liquid goes through them that then moves that energy into a storage tank. And then they're trying to balance losing heat back to the environment, right? So you have a nice little energy balance there to the right, energy coming in. You've got some reflective losses right off the get-go, right? We're under glass will not let 100% of solar energy through. We, in the solar business, flat plates, we use low iron glass, so it actually lets over 90% of solar energy through, versus kind of standard window glass is around 70%. Right, that's why in windows and different things, you want to stack them up to really kind of break down that solar energy input, keep the heat coming through the window. So there's different efficiency curves depending. These are based upon gross area. So, but they decline at different levels. So an evacuated tube collector, we'll talk about it a little bit more, has a vacuum insulation, so it can lose less heat with higher temperature differentials. So it has more of a flatter line. As far as the efficiency curve, it starts out a little lower because there's some loss in gross area between the tubes and different things versus a flat plate, but it can carry out longer. So if you can kind of see a crossover point between the two technologies right around 125 degrees Fahrenheit, that's the differential between ambient and collector input temperature. And so that's usually right around 180 degrees Fahrenheit if you're thinking about your application temperatures. So we see a crossover in these two technologies and maybe start looking at one versus the other if you happen to need those high temperatures. So this is a glazed flat plate. SunEarth, this is actually what we make. And so it's a fairly old technology. It's been around since 1800s. Fairly simple. You take some black metal, piping, you put it underneath glass inside an insulated box, and you pump through it. So there's been advancements over the years, but that's pretty much the basics of it. Right? So we have to use, like I said, low iron glass. It's tempered, so if it gets broken, it goes in a million pieces. Use copper passageways, normal polyiso and fiberglass type insulations. These units, they're actually made to also breathe. And so there's vent holes and different things to allow condensation and other naturally occurring things that you can't really keep from happening for decades, out in the environment. Just make sure you can clear it out nice and early. So evacuated tubes are the other technology we talked about a little bit in the medium temperature range. So they have a kind of a heat pipe generally designed. So there's a fin with high efficiency coating surface on it, and then there's a header pipe where the fluid is being pumped, right? So the heat will rise up into that header pipe and get pumped off to its source, right? So the tubes themselves are double glass, so there's vacuum insulation in between in order to optimize that, reduce that heat loss. You'll notice there's happens to be gaps, though, in between each one of the tubes if you're looking straight on. So that's generally, if you looked at the efficiency curve earlier on a per square foot basis, kind of lose that a little bit. So that's what shows up in the efficiency curves. All technologies work great for hydronics and work great for domestic water heating. One thing about evacuated tubes is you can see they generally what we call the stagnation temperature, or is it the system turns off. What happens to the panel and what happens to the temperatures, they tend to go run much higher. So you have to account for that in your system designs and different things like that to make sure that your fluids and your other things can handle those sorts of temperatures. So on top of the per square foot, solar to solar, right? We want to talk a little bit about some of the advantages of why solar thermal would be advantageous as far as an energy source for hydronic applications. So they require very low pumping power, generally around 1 gallon per minute, as far as a flow rate per collector. The generation of the collector really depends on the ambient temperature and how much sun is out, different things like that. It's variable, but if you're just trying to estimate pretty quickly, if we're going to look at about 200 BTUs per hour per square foot, right? The solar energy is around 318 BTUs per hour per square foot in full sun. So if you take that with a nominal about 25 watts per panel, like when you get to larger systems, that can go down dramatically to 5 or less watts per panel as far as required pumping power. But if you're running kind of basic back of the napkin COP calculation, you have a 58 watts per square meter collector for a 4 by 10 or 40 square foot collector, 25 watts of COP around 95. Right? So the amount of energy that you're putting into a solar thermal system for the amount of energy you get out is pretty tremendous. And that's really a huge advantage for a lot of heating systems to take advantage where solar thermal technology can pair well. So there's a couple things to identify for hydronics technologies. So hydronics technologies are generally for heating loads, right? And heating loads is generally in the winter. And so in the winter time, we do a few things differently for designing a system to integrate with the hydronic system. So you increase the angle, right? Try to catch more of that sun, that winter sun, the lower sun. So it raises the collectors up. It also helps with overheating. When the sun's high, not as much of that solar energy is beating down on the collectors, so it controls that for certain system types. It also improves snow slough off. So this is actually an installation up in Squaw Valley, California, on a school. It has a hydronic system, and so all the snow built up in the front is actually being sloughed off from the collectors at the top. So flat plate collectors are very good for this. Single pieces of long glass, they lose some heat, which allows that to break the ice pack and not to slide off. So, evacuated tube collectors tend to sometimes hold on to that snow. So if you're in a snowy environment, it might be worth looking at, even though you may believe it's colder and evacuated tubes may be advantageous, depending on your snowpack, you may not clear the panels off. Similar with PV modules. This happens to be a Combi installation. So the solar thermal also allows the PV. When it falls off the solar thermal, it pushes it off the PV on the ground. So it keeps everything really exposed. For those nice collectors at the top, this is a drain back tank, so this is sort of designed when the circulating pump stops. All the fluid in the collectors, which is exposed outside in the pipe, can be stored in the drain back tank in conditioned space. Have an external heat exchanger, also pumping over to the buffer tank. Buffer tank then goes whether through heat injection or directly into the heating loop. Right there. So for hydronic applications, one of the things we can do is size that buffer tank a little smaller than we would on domestic water heating applications. Because generally all of the heat that we can collect, we can use right then. We don't really need to store it for later. It's cold now, it's going to be cold later. Let's just get it into the home, get it into the stock, get it where we need to get it. So instead of our normal 1 to 2, maybe, collector to gallons of storage, we can do 1 to 1 or even 2 to 1. Right? The big advantage in this is that we can do is that the heat is pretty slow, right? It's not really fast. So if you have like a slab type system, and if you're using a slab sensor instead of using a thermostat and an air sensor, you can continue to heat that slab like during the day instead of storing that energy to try to heat it, pull it out later when the air temperature happens to drop or somebody comes home from work or anything like that. So there's a couple in the solar thermal arena. There's some products to make that a little easier. Instead of all those pumps and heat exchangers and different valves and stuff, depending on your system size, you can select pump stations, we call them, right? Have external heat exchangers built in for different size collector arrays, and everything's already kind of done for you. So for combi tanks, that's generally where we're putting the heat exchangers inside the tank itself. So this is a great example of that. We have, again, another drain back system. It's very popular in hydronics to use drain back systems because during the summer you don't have to account for all the heat generated for an indirect system. You can drain the collectors out. You don't have this runaway heat on your solar fluid. So we have a drain back tank here on top of the storage tank, low coil with your solar circulator, and then a high coil for your hydronic projection. Right? So the controller can decide what's going on with this tank and what's going on with the loads in order to pump into that circuit. And even if it's a preheat, you can go through the boiler here and then out. Still saving a lot of energy even if it wasn't to the temperature that you needed it to. So we have here is a multi-load tank. So in this particular version, there's coil heat exchangers built into the tank to serve the different loads. And that is another drain back design where we have collectors. This is your drain back vessel, it's unpressurized. Right? So it's your drain back vessel and your storage vessel all in one. As we kind of mentioned, for hydronics, the systems are generally sized for heating loads, so then when it comes time, if the heating season's over, you still have a lot of energy potential. So if there's some other places on site you can use that energy, that heat energy, this is a great way to do that. This design is not using three-way valves, right? I was taught a long time ago that if you can, don't use a three-way valve. In solar thermal, they're generally very passive systems, and so pumps, if you use mechanical equipment, pumps tend to last a little longer than three-way valves. So this one's using all pumps. And so this has different priorities. You can see it's servicing the radiant, the domestic hot water, and a pool or a hot tub. So when the winter time's over, now you can heat your pool with that same array, not losing any of that potential. So go through a project here by Resolution Energy up in Colorado. This was a single family home, 4,200 square foot, with a radiant system to service multiple loads, using four 4x8 collectors. So I guess to mention in that, generally in solar thermal, there's a much bigger load than there is space to meet the load. Yes, sir.
There in Colorado, what's their design ambient in winter?
I don't remember that particular one. I mean, Colorado varies so much. But I guess one of the things about Colorado is they have a lot of winter sun, right? So solar thermal tends to work well, even though it's cold. So this is the system design. It's a integrated buffer tank type design, Combi Tank, drain back circuit, has a low collector to storage ratio of 1 to 1, and has a heat injection design. So if you notice, all the solar sort of circuits happening over here, and then what was normally, this was a retrofit, so it wasn't designed originally with solar thermal for the radiant system. So you have your radiant boiler and your heat exchanger going onto your loop. And what they did is they inject the heat just by pumping through two closely spaced T's, which we're used to doing in the hydronics business, right into the loop to get your heat where you need it to be. Key is, again, in this, is controls. Just make sure that it's looking, you know, if you have heat in the solar tank, use the solar tank. If not, you use the fuel boiler. Here we have kind of the energy graph of that system. The blue lines are what we call solar fraction. And the solar fraction is the percentage of the solar, the percentage of the overall load that's being met by the solar power, right? So if you had 100% solar fraction, that meant that all the load, all the energy needed for that system was being met by solar energy. Generally, that's not the case. We really don't want that to be the case. If that is the case, that means you even had energy when it was cloudy and dark, you know. So the system's generally way bigger than it needed to be. But depends, that could be a useful thing. So you can see the profile here, kind of the winter profile of solar fraction, fairly small within the summertime, where it's just the domestic water heating. And you meet pretty much all the domestic water heating with that system. It's much really bigger than the domestic water heating system needs to be, and back down. So that 4x8 collector system ended up doing about 10% of the energy for this particular residence, which they were really happy with. There's more potential there if they wanted to add more collectors, but you can see you end up with this real excess in the summer. So what they did is actually came back later and tied in a hot tub in order to take advantage of that energy, you know, more year round. So that is one of the main points for hydronic systems is if you can identify another revenue stream.
Is thermal expansion an issue when you're in a low draw?
Thermal expansion, yeah. I mean, so our system, the system designs, they can heat up quite a bit, right? Almost 300 degrees Fahrenheit. And so you have to account, and usually depending on the system design, you have phase change and different things like that. So in drainback systems, it's not really that much of a concern because what's really getting heated to those temperatures will be air when the system shuts down. But in closed loop or indirect type glycol systems, yes, we have expansion tanks to install on the solar side. Generally run fairly low pressures, 15 to 30 psi. We're proponents of, on those type of systems, steam back designs. And what that means is you actually allow the collectors and fluid in the collectors to steam into the expansion tank. So it usually requires a much larger expansion tank than just standard fluid expansion. But that helps protect that fluid from degradation from the high temperatures in the collectors, especially during the summer times and different things where they'll be stagnating for long periods of time. So
Thank you.
Same with the storage volumes, right? If it's a pressurized storage volume, they're generally bigger. You need expansion tanks to take up that temperature difference from there. So I keep it pretty brief for this morning. Hopefully we have some questions in order to continue to talk. But thank you very much. Yeah.
It was actually in Conifer, Colorado, Jefferson County, the job reference.
Okay. Thank you.
That helps all.
Prevention from freezing, does that on its own?
So yeah, you do that through the system design. Right? So if you're using a drainback system, which are most of the systems we showed here, it keeps it from freezing is when there's no solar energy available, right? The fluid drains out of everything that's external to the building and structure. So and that keeps it from freezing. Or you use glycol antifreeze solution. Yes, sir.
So is it more difficult to design a drain-back system if you're using evacuated tubes?
Not necessarily. The evacuated tubes can be designed to work that way, right? The key is that you need to make sure that everything is sloped during, right?
Like heat pipes, so that
The heat pipes don't have fluid in them. So they're essentially just the heat is migrating up the pipe into a bowl.
does that bowl overheat though then?
It can, yes.
Anytime in summer?
Yes, it can. But they're designed to take stagnation temperatures. That's the manufacturer's job. There will be time when it can just be there, but it can be a problem.
And what do they use in that? Is it like a refrigerant
Usually it depends on the manufacturer. It's not usually refrigerant, but it can be, could just be air. I mean, just natural convection. Any other questions?
How does it, what sensor or how does it know to drain back when there's no solar?
So solar thermal systems work on a temperature differential methodology. So there's a sensor installed up at the collector, right, to measure the collector temperature, and there's a sensor down at your tank or your heat exchanger where you know your load. So when the roof is hotter, right, then it will turn on. That means the sun's out, right? And when it's not, or when the temperature differential shrinks too much, it will collapse and then it will drain back. So depending, on the environment, in Colorado, when it's sunny, it's usually the temperature, the collectors can get pretty hot and the snow comes off really fast. Up in the Northeast, for instance, the snow's really heavy, right, and tends to stick to things. And so they actually like to put a little bit of antifreeze in their drainback systems. So as you pump to the roof, part of the collector can still be covered in snow, even though it's hot, the top of it's uncovered, right? And collectors for hot plates, they can fill from the bottom and then the heat comes out from the top. And so that way they still protect them from flash freezing, essentially. But the temperature differential being measured is how it dictates whether it should turn on a pump or not, and whether it can potentially freeze.
But it's all automatic, so when the sun's back,
Yep.
the next day, it's gonna
Kick it back on again. Yep.
it's gonna pump it correctly.
Yeah, and the controllers have also limits, so you could program in your controller if it's not a 70 degrees, if I'm not measuring 70 degrees, or I'm not measuring 45 degrees at that sensor, even if my temperature differential is met, it still won't turn on.
Do you install a lot of these in Fontana?
In Fontana? No. No. Fontana, I mean, we're a desert, kind of climate, and the radiance is actually not very common. For solar thermal, one of the challenges is it's replacing the heat energy, right? And so whatever that cost of heat energy is then what your return in your economics, how that work.
What's the best climate for these?
I mean, some climates are the best, but they work everywhere in the latitudes of the United States and below, right? There really is not a bad region for these in the United States. They work north to south. But in the kind of sun belts is generally where you get the most sun out of it.
But you always do a backup, a gas boiler, heat pump or something?
Yeah. You always need backup, and you never know when the sun's not going to shine, right? These are also generally fractional systems, so they're not sized to meet the whole load. If they are, then they end up being very, they end up being very big, right? And sometimes that can be prohibitive. And so we always have a backup. And they work also well with all backups, right? Whether that's electric resistance, gas boilers, heat pumps, it doesn't matter. It's another heat source to go into the system that happens to be a fairly efficient way to do it. So you can compare them together. And they don't need, as long as you know the advantages of each, they don't have to fight. You just got to control them to allow each to do its own best work. So
How well does this scale to a commercial application?
very well. The collectors are pretty much the same, so you can just manifold up more and more and more. So we have systems of hundreds of collectors on them in large tanks in order to, and that works well. But most of the cost in these systems is the labor to install them, as most things are, right? And so running one size pipe versus 2-3 size pipes up, it's about the same. So the commercial is where you see a lot of real benefit, or larger systems, which is also why it works well in hydronics, because they are larger system versus a standard water heating system residentially. Yes, sir.
In a solar system like this, in a residential, can you run the hydronic system on floor hydronics and also use the cooling system?
Use the solar for cooling?
Well, I heard this is a system that nowadays, in the old days, they have, we can only use it on floor hydronic heating, and it was almost impossible to actually cool the house with a chiller through the system.
Yeah, I mean, this doesn't affect your standard hydronic system in that way, right? You know, you just have to have the controls not have it heated when you're trying to cool it, but there's nothing keeping this from working in a combination heating and cooling system.
And the north, if you build a system in the summertime, of course, you have extra heat, right? That's what you were saying, that you need to put in maybe put a hot tub, whatever. In the wintertime, now there's going to be more heat, right? Correct? So if you design a system that's just actually over the needs, can you have a zone where you can dump heat into the outdoor driveways and things like that to keep?
Absolutely. And that we've had installations for heating, you know, in Alaska and different areas where they'll dump it into, you know, sand built underneath, or a big tank built, you know, or rocks sort of cover, or even a combination of geothermal systems where you can help heat the ground to pull that out later, right? So you know, it's advantageous to try to figure out if there is a good slick way based upon the installation to capture that summer heat for use later. But that's a good way to do it, is to get poking around. Yes, sir.
Can you run some of these collection systems at night in the summertime and get re-radiation?
So
to cool them down and run for cooling?
So yes, I guess would be the answer, but they are not really designed to do that very well. So it is possible to do it, but I can't tell you how much energy it's gonna help you, right? So that is another thing to be concerned about regarding freezing of collectors, and bringing it up, is that they do radiate at night. So that means that they can freeze it at lower than 32 degrees Fahrenheit. In Fontana, because we have nice clear night skies, not much cloud cover, even though it was 50 degrees outside, it's been below 32 on the collector plate itself. So that's important, you know, if as you're going around, it doesn't freeze here. There's maybe, you know, very few freeze events, but collectors themselves, they have very low thermal mass. It's about 1 gallon in one of those, and they like to give off heat, so they can work in that way. It's just generally not worth the complexity, because you don't get that much energy from it in cooling applications in those types, right? There are unglazed types that can be used for cooling applications and different things like that. It work better to reject heat to the night sky.
Is this technology used more in domestic hot water heating, or
yes, I mean,
more than the actual heating?
Yes, I would say, you know, if you look at all the solar thermal systems installed in the U.S., the majority of them are installed actually on cool heating, but then domestic water heating would be next. Okay. Yes, sir.
A question about the different storage types. How often would you say you see systems with unpressurized storage versus on-board versus?
Yes, so there seems to be more unpressurized storage happening. Historically, it was a pressurized sort of system, right? Pressure tanks with coil heat exchangers and things like that. But we are seeing a progression towards unpressurized storage in solar thermal, especially in large-scale solar thermal, because the tanks can get very expensive. ASME rated, big pressure vessels. You know, everybody also knows steel costs these days if you're trying to price out jobs and different things. And so unpressurized has a lot of advantage in that, where you don't actually need the water, you just need the heat.
And what manufacturers do you typically work with, you want to say, like for the unpressurized tanks?
I mean, there's a few. It's still kind of a niche market, I would say. But there's Hydroflex Systems, which is kind of out of Pennsylvania. There's STSS. There's Multiload Manufacturing, and I'm sure there's more, but it's not a few ones come on the top of my head. But you know, they generally tend to be insulated, you know, above-ground pool type, I'd call it, if you want to call it that way, right?
Breaking the pieces, right?
Yeah, and that's another good thing about them. They're collapsible generally. They design to be collapsible, so it can be site-built. It's usually, you know, if in a retrofit application, you have a door like that, you need a few thousand gallons to get through it. You know, in a pressurized world, you break out the door, right? And then that's how you did it. But now with unpressurized tanks, you can get them in pieces, build them up, and take care of the pressure substitutions.
Is there any seismic concern? I know you need seismic bracing with.
Yeah, of course.
It's the same point?
Yeah, I mean, it's going to be very similar. I mean, one advantage you have is you don't have all the steel built into it. Like, they generally tend to not be tall vertical tanks. They're kind of short, squatty tanks. So that helps. But, you know, like any tank size is concerned, it's a big body of water shaking around. If there's anything else, I really appreciate your attention the first thing this morning. And it's been a great talk. Thank you.